Okay, it's recording. Yeah. So it's my pleasure to welcome Nham from University of North Georgia. We'll talk about restricted partitions and SL2 cohomology.
Oh, well, thank you, Scott.
Yeah.
Okay, thanks. Well, thanks everyone for coming here and listen to my talk. It's my pleasure to be back here and meet with some old friends. Okay. I'm going to talk about restricted partitions and we're going to apply some results of this subject to find the cohomology to get an upper bound for the dimension of the cohomology of SL2. Okay, this is a joint work with Stephen Benzel, Scott Connor, and Ken Pham. Stephen Benzel is my college at UNG. Scott Connor and Pham are students. Pham already graduated. Scott Connor is still working with me on a senior project, and he will be finishing a bachelor degree soon, and will be applying for grad school. Okay. Well, honestly, this is just undergraduate project with a little bit flavor of graduate study. Okay, so well, let me just give some definition about partitions. Okay, so I know that partitions can be defined in many contexts. Here we focus on integer partitions. Okay, so that means for any integers m, okay, a partition is a sum of m written as alpha 1 plus alpha 2 plus etc. to alpha t. Okay, so here alpha 1 less than or equal to alpha 2, so less than all the way to alpha t. Well, this means that all the alpha i's are not necessarily distinct. Okay? And okay, so here, and they are all in integers, okay? Positive integers. Okay, so here every alpha I is called a part of a partition. Each alpha I is called part of the partition. And T is called the number of parts. Okay, and restricted partitions come from restricting the parts of the partition or the number of parts of the partition. Okay, so in this case, we're gonna require both. Okay, so we're gonna call a partition. Well, I'm gonna let A be a subset of positive integers, and is a positive integers. Okay, so then a partition of M is called restricted. If the parts belong to the given set A, and the number of parts T is at most N. Okay, so we are interested in this special type of partitions of N. Okay. One big problem about this type of partitions is as follows. Okay, so we have this problem right here. Okay, how can we estimate the number of such partitions in terms of the number n and the set A. Okay. So here we want to estimate it for all the integers n. Okay. Well, to be short, from now on I'm going to denote this number of partitions is P of m n A. Okay, so this number depends on m, n, and the set A. Okay. Well, in general, this problem is very hard to solve. You cannot tell anything about this number if the set A is arbitrary and is any positive integer. Okay, so and very little is known in solving this problem. We could only find 2 papers related to this problem. Okay, one of them is from Kenfield. With in 2012, and the other is from 2014. Okay, well, note that Kenfield is a emeritus professor of Department of Computer Science here. Yeah. So this is saying that, okay, this problem has some application in computer science, but that is not in the scope of this talk. Okay. Well, they particularly focus on the growth rate of this number for the certain type of the set capital A. Okay, that's pretty much all we could say about this problem. Okay, well, we are not an expert. We are not experts on this subject. We do not have ambitions to solve this problem. However, we saw that there is some connection between this number with the dimension of SL2 cohomology. In particular, or roughly speaking, if we can find an upper bound for this number right here, then we should be able to construct an upper bound for the SL2 cohomology with coefficient in the Weyl modules. Okay, and that's what we are focusing on. Okay, so we want to get an upper bound for this number right here. Okay. All right. So now I'm going to show you what we found on this problem. Okay, here is what we have right here. Is everyone okay with my handwriting? Okay, good. Okay, so if the set A, okay, if the set A satisfies some certain condition, then we can obtain an upper bound by the Fibonacci number. Okay, so it is stated as follows. So the set A, suppose that the set A has the elements A1, A2, etc. Okay. All of them are written in an increasing order. Okay, and you see in the positive integer set. Okay, and satisfied. Satisfy the following condition. Okay, so if you have 2a sub s minus 1 plus 4a sub s minus 2 plus all the way to a 1, A is 1, less than A sub S for any S greater than or equal to 2. Okay? Then we have the following. The number of restricted partitions into at most n parts from the set A, okay, will be less than or equal to f sub n. Here f sub n is the Fn is the nth Fibonacci number with f sub 1 equal to f sub 2 equal to 1. Okay, so here is the starting point of this Fibonacci number. Okay. Well, the proof is elementary. So I'm gonna quickly go over it as follows. Okay, so let's let this condition be the star condition. Okay, and I'm gonna proceed by strong induction on n. Okay, so we're going to do strong induction on n. Okay. Well, note that this bound doesn't depend on n. This is for any n, so we can call it a universal bound. Okay, and all right. So base case. Okay. It's easy to see that okay, if you partition the number m with one pole, then just one way, at most one way. If you try to partition it into two poles, now let's take a look back to the condition star right here. The condition star will prevent you from having the following situation. So A sub S cannot be written as two of that, and cannot be written as that. Okay, so basically the condition star will tell you that, okay, in order to break it down into two parts, or at most two parts, you still have only one way at most. Okay. Well, this is a little bit interesting point right here. I need to consider two cases here for the induction, because if you only have to take a look at one case, then you don't know if this is F1 or F2. Yeah. So for dealing with Fibonacci number, you really need both the first four cases. This is okay. Right. So that is the base case. Okay. Now we assume that is true. Okay. The inequality is true for any t less than n, with n greater than or equal to 3, okay, because we already covered the first two cases. Okay. And now, running out. Okay. Oh, I forgot to check with you that how much time do I have for this talk? 15 minutes. 15 minutes. Okay. Thank you. Okay, so now we want to show that P's of M and A less than or equal to F sub N. Okay, so now first of all, I'm going to fix an N, okay, and let AS be the largest number in A such that A sub S less than or equal to M. All right. Well, with this setting, then we can identify the number of such partitions with the following. It's going to be the number of solutions. X1 all the way up to Xn in and to the system, to the following system right here. It's going to be I, A sub I, with I going from 1 to S equal to M, and the number of pores going to be less than or equal to N. Yeah, we're just rewriting the partition into the solution of our system. Okay. All right. So now, I'm gonna use the condition star here to break down the number of partitions into the following cases. Okay, so note that if x sub 1, well, x sub s is 0, x sub s minus 1 less than or equal to 2, s of x minus 2 less than or equal to 4, etc. Okay, and x of 1 less than 2, s minus 1. Then we know that this sum is going to be less than minus 1. And this is really less than A sub s, and less than or equal to N. So that means no solution. So in order to have solutions, we're going to need, okay, so to have solution of this system right here, let me call this system I, we need the following. Okay, so we need either x of s greater than or equal to 1, x of s minus 1 greater than or equal to 3, x of s minus 2 greater than or equal to 5, etc. all the way to x of 1 greater than or equal to that. Okay. All right. So, well, this is the or here. Okay. This is and. This is or. We do the conjugation. Okay. So now we're gonna from here for each condition right here, we're gonna do the change of variables to this system right here to produce the a version of the P of M and A. Okay. For example, because of this, I'm going to do the change of variable that I'm going to let x of s equal to x prime of s plus 1. Here, x prime of s is a non-negative integer, okay? And so, with the number of partitions restricted to this condition right here, you can use this change of variable to rewrite this system. So it's going to be this xi a sub I from 1 to s minus 1, and this is x prime s a sub s right here, and with m subtract a sub s. Okay, and this with this replaces by x prime of s. You're going to have the condition with I from 1 to s minus 1 xi, and then plus s prime equal to n subtract 1. Okay, so basically, if you restrict the number of partitions with this condition right here, right, then you're going to end up with p of m subtract a sub s. I'm going to this thing right here say that, okay, the p, m, and a restricted to the condition x of s equal to 1 or greater than or equal to 1 right here will give you p's of m and minus a s and m minus 1. Good. Okay, and we're going to do this for all the conditions right here, and we're going to end up with the following. I don't want to erase anything of that. So can I use this book? Okay. All right. So now.
It's not possible to see from this side of the room.
Oh. Well, can I use the whiteboard?
See that?
We have. It's good to have the alternative here. Okay, so then we have p of less than or equal. Well, we have less than or equal because, well, you might have one or more of these conditions. So it's going to be this.
Those are non-chemical, so black marker.
Oh, okay. Yeah.
The thing, they have the thing, none of those equals one of.
Non-erasable.
No, there's one. Let me show you which one. You can go
Right.
which one it is. That.
Oh.
There you go.
Okay. Okay. M minus 4. I need to be consistent here. 3a so s minus 1a actually all the way to p m 2s minus 1 a1 and subtract 2s minus 1 a. Okay.
What's the second term?
Oh yeah. And subtract 3. Yeah. Well, now we use inductive hypothesis to get that this is less than f sub n minus 1. Let's say f n minus 3 and minus 2 s minus 1. Okay, and now there is a special property of Fibonacci sequence. This is very elementary, but it says that okay, the sum of all the Fibonacci's numbers at the odd spot will be equal to this, and the sum of all the Fibonacci number at even spot will be equal to this. Okay, so basically the two equalities here implies that if you do the sum of, okay, if you do the sum of all the and subtract 2i with I going from 0 to all the way, you can do in 2, 1 something. It's going to be less than or equal to f sub n plus 1. Okay? And so this is just nothing. And that is just the inductive proof of the theorem. Okay. All right. Now I'm going to go back to the theorem. We can erase the proof now. Well, basically the theorem say that if the set A have the elements that are not so close to each other, then we can obtain the Fibonacci upper bound. Well, now the question is if such a set A exists. Okay. Well, actually, there are plenty of them. Okay, there are plenty of them. And here is another thing we find about this. Okay, so let Q be a positive integer and A sub Q be the set of all the powers of Q. Okay, then we have the following. The set A sub Q will satisfy the condition star for infinitely many values. Okay, so then if Q is greater than 3, then AQ satisfy the condition star. Consequently, we have the number of partitions of m into n at most n pos in A sub Q will be less than or equal to the Fibonacci number f sub n. Okay. And this is the key result for us to apply to the SL2 cohomology and find the upper bound. Okay, so yeah, this is the end of the first part about restricted partition. Let me pause for a second to see if you have any questions. Okay, well, now I'm going to move on to the second part of the talk. We're going to apply this result to get an upper bound for SL2 cohomology. I forgot to put part 1 to cohomology. Okay, so well, first I need to tell you why we are considering the SL2 cohomology. Well, the ultimate goal is as follows. We would like to find a universal bound for the cohomology of algebraic group G with coefficient in any module M. Okay. Algebraic G and G module M. Okay. Well, by universal bound, I mean this only depends on the degree n. Okay. Well, actually, Dan and his co-authors did a series of work to show the existence of this bound. And if I may ask, is there any update about finding explicit universal bound for the rational cohomology of algebraic group?
I thought, was it Leonard and Brian? I thought they did some work on this.
Did some work on it.
I'd have to think back on
Yeah, but well, as well,
it.
Yeah.
I'll take a look.
yeah. Well, I mean, from what we found is, well, I think I remember the work of Scott and Marshall.
Yeah.
You mean like 10 years ago or so?
Yes.
Right. Yeah. Well, they, I don't think they come up with a specific bound, but they show the system, and they emphasize that it's interesting to see if there is an explicit bound. Okay, and that motivates our work right here. Okay. Well, well, this is a huge problem right here, and well, we didn't know how to tackle this problem at the beginning. Okay, so the good starting point is to work with SL2 and see if we can come up with a universal bound in that case first. Okay, and then try to generalize for finding the bound for any algebraic group. Okay, so say SL2 is the first attack. Okay. All right. Okay, so I'm going to fix some notation for this part. Okay, from now on, we're going to fix K at the ground field, which is algebraically closed field. Algebraic. Closed field. Our characteristics P. Well, SL2 is the algebraic group or group scheme defined over K. Well, with the SL2 situation, we have very nice structure for the Weyl lattice and the dominance Weyl lattice. Okay, so basically we have the Weyl lattice is the same as Z and dominance Weyl. It's going to be the same as the natural numbers, and this is the link for us to use the number theory results to work with the cohomology right here. Okay. and we denote V sub n, the Weyl module over SL2 with highest rate. Yeah. And we are interested in bounding the dimension of the cohomology of SF2 with coefficient is the Weyl module. Okay. There's a little bit history about this problem, and I'm going to show you a few results that related to
Just to back up for 1 second, for your ultimate goal, n is n indecomposable or your useful, and n would be really a direct sum of things, of course. So that
am
in your on the upper left board.
right here.
Yeah. Is n like
The module am, they're really, well,
you can take a direct sum of a bunch of copies to get a really big.
yeah, I think the focus is on the simple or indecomposable modules. And yeah, the reason we look at the Weyl module is indecomposable module. Yeah, we focus on indecomposable module. That's right. Thanks.
So partial and Scott actually have a universal bound for simple modules.
For simple module.
They have a universal.
Oh. So the universal bound, that only depends on the degree n,
Yes. that's-
not on the rank or the
No, it does
characteristic.
depend. It depends on the root system
Oh.
and the degree
The root system and the degree.
of the cohomology.
Oh, okay. So,
So they,
but there's still, so that means that this question is still open, because we look for the bound that only depends on the degree n.
yeah, so I mean, so their result is only for simple modules.
Yeah. Okay. I got it. Thanks, Ken. All right. Okay. So, yeah, some history.
But just to back up for 1 second, I can't remember what you were saying about what Dan has covered. But is there a bound for n and for any group? I mean, I would think if the group got really large, that you might possibly get a large dimension of the cohomology for some fixed n.
Yeah, so the bound does depend. It depends on.
Depends on the root system as well. That's
Right.
a partial, yeah. So,
Yeah, that's
so,
right.
so it's not, so
That's
it's, so it's, oh, right, so, okay, so the bound that depends on G as well.
Yes.
Oh.
Absolutely. It does
Good.
depend.
It has to have.
Yeah, we did this AIM conference, right? Even for like H1, I mean, it's, it's going to depend on like cardinalistic elementary stuff. Even
For-
there, with the root system getting big.
Right, no, that's what I was asking.
Yeah.
I was thinking that it would depend on.
Yes,
Oh, okay.
it does depend on the root system.
Yeah. All right. Well, anyway, yeah, we can go back on the problem about bounding the dimension of the cohomology of SL2. Well, here are some results that I found. Okay, so Edmund in 1993. Okay, she showed that the dimension of the actination space between Weyl modules is less than 1. Okay. And a few years later, she and Cox in 2000 show the degree 2 extension of the Weyl module. Here m sub 1 and m1 and m2 are arbitrary integers. Less than 2. Okay. Well, and then Hannibals. Parker. This in 2013 show that if you take the maximum of the dimension of the this this max, this sequence will grow exponentially. Okay, so well, we in 2018, I worked with some colleagues at the University of Arizona. And we did some computation and we confirmed that the dimension of the extension of degree 3 between two Weyl module less than or equal to 3. Right. So now, well, I think this. Well, I think from here you can sort of guess the bound that we are trying to get right here. Well, this is 1, 2, 3 right here, and it must be exponential growth. So we saw that, and we made a conjecture that the dimension of the n degree of the n degree extension between Weyl modules going to be less than or equal to the n plus 1 Fibonacci number. Well, if you look back there, 1 is the f sub 2, 2 is f sub 3, and this is f sub 4. Okay, and in the same paper with Lux and Zan, we show some evidence supporting this conjecture right here. And yeah, we was able to show this. Okay, we were able to show. For well, the dimension of in degree cohomology of SL2 V sub m is less than or equal to, okay, there's two things here. This, if n is less than or equal to that 2p minus 3. So basically, it's true for small n degree n. And if n is big, then we were able to get it bound with the following huge number let me see, it's going to be n plus 1 to the n plus 1 e to the 2 pi n plus 1 over root of 3. Yes. Okay, so basically we was not able to prove it to this cohomology dimension bounded by the f sub n plus 1 for all the case. Okay. How much time do I have left?
6 minutes.
Oh, okay. Well, well, let me try to be quick right here. Well, the way we try to prove this is the following. We're gonna identify the dimension of x of n of the Borel subgroup of SL2 this. Okay. We identify it with the number of solutions to the system as follows. So this is B1, A1, B2, P, A2, A, R minus 1 plus BR, P to the A to R, P to the R, equal to M. M over 2, and this is B1 to BR equal to N. Okay. Here is AI belong to natural number, and B sub I is just either 0 or 1. Okay. Okay, well, and from this identity, well, we then show that the dimension of the n degree cohomology of SL2 of Vn is the same as the dimension of the degree n plus 1 cohomology of the Borel subgroup. That. Okay. Okay. Well, here, if you rewrite this equation in terms of the partition, well, by letting say d sub 1 equal to a1 plus b2, or d sub this is d dr minus 1, and this is dr right here, then this system can be rewritten as the system that is similar to the one we have for computing the partitions. Okay, so this is the link right here to the number of partitions right here. Okay, and well, of course, in this case, this is not simply the same, because the solutions really depends on this extra variables right here, the b sub I. But we can do some modification of our proof with the restricted partitions to come up with a bound for this Borel cohomology, and that will deduce the upper bound for the SL2 cohomology. Okay, so finally we come up with the following results. Okay. We have the dimension of the cohomology of SL2, Bm is less than or equal to the n plus 1 Fibonacci number if the prime p is bigger than 5. And this is, and in the case of small primes, we have a larger bound.
You raise that up, we can't see it behind that. Raise the board up so we can.
Oh, yeah, sorry. Yeah. So this is about we could get right here. Well, no, there a little bit of a remark I need to make right here. For p equal to 2, we found an example that the dimension of this cohomology is greater than that number right here. So this bound, I think, cannot be improved for the case p equal to 2. But for the case p equal to 3, we believe that it should go up here. We should still have the n plus 1 Fibonacci number. Okay, and now in the very last minute, I would like to make some application to the bounds for the algebraic group of higher rank. The eraser for so I forgot to close it. Alright. Okay, so let's assume p greater than or equal to 5. Then we could obtain a linear bound. Okay, so we could obtain, there is a linear bound for the SL2 cohomology as follows. The dimension of SL2 cohomology with any module m over SL2 will be less than or equal to absolute n, the dimension of m. Alright, this is a linear map. And even though we couldn't, we didn't put this part in the paper, but we may have get for a linear bound for any simple algebraic group. Range on G and module M over G. We have dimension of this cohomology less than or equal to the Fibonacci number, the n Fibonacci number to the power of r, the dimension of n. Okay. Yeah, it still depends on the rank of. We wish to generalize the result to have the result for some specific module M, for example, indecomposable or simple module, and we would like to get rid of the dependent on the dimension of M. Okay, that would be a good thing for the universal bound of the cohomology. Yeah, I think I should stop here. Thank you everyone for listening.
Any questions?
Yeah, so the second thing after the method, so that follows by circularity.
Yes, that's
And you
right.
could use your speckle sequence.
That's
actually
correct,
before.
yeah. Yeah.
So in general, this will work for any B and any G. And so then you can actually bound. So we know what the B cohomology is up to degree 3.
Up to degree 3,
Yeah.
yes. In your paper with Pham and
And also Carolyn writes.
Yeah.
So that means you can, for any Weyl module up to a certain degree, you can bound the cohomology using those bounds.
we can have a bound.
At
And
least for the low degree bounds.
yeah. So in that case, the bound will not depend on the degree n. It just,
Yeah, it won't depend on the degree.
Yeah.
That's good.
but it still depends on the rank of the group G.
Not for the low degree.
Not for the lower degree. So that's what I hope for. I hope for that for higher degree, we still can find something independent of the rank.
Right.
Yeah, thanks for letting me know. Yes.
How tight are these bounds actually in practice? Like, are you actually getting close to Fn plus 1 quite often for values of m, or is it?
It is tight. It is tight for low value of n. That's what we could verify by computer. But higher than that, we are not sure. That really depends on the proof, because when you go for any m, I erase it for proof. I erase it to proof. Yeah, I'm not sure. We haven't done any calculation in high value for him.
So do you know they're not polynomial in
It's not polynomial. Yeah, for sure, because of this. Yeah, we know that it has to grow. Exponential rate. And yeah, the m here can vary. That's the big problem right there, and can be anything.
Oh, so I'm looking back at this old paper of ours from the AIM conference. And so if you take H1 for any algebraic group, so if you take H1G of it, there's a linear bound.
There's a linear bound.
And it's 1 over the Coxeter number times the dimension of that.
And that is for any algebraic group.
Yeah, we actually proved that.
Okay, but that form for the first degree, do we
Yes.
have for second degree?
We do have one for the second degree too,
Yeah.
and it's also linear.
Yeah.
So, now the question is how good can you do? So
Yeah.
I'll show you the paper later on.
Yeah.
Okay.
Other questions? If not, let's thank the speaker again.
Thank you.